Welcome to the fascinating world of nested data structures. Imagine organizing data like a spreadsheet, rows and columns of information. Or like a building with multiple floors and rooms. Today we'll explore 2D lists, matrices, and complex nested structures that let you handle multi-dimensional data with ease. From game boards to image processing, from data tables to mathematical computations, nested lists are your gateway to sophisticated data organization. Let's dive into this multi-dimensional adventure. Nested lists are lists that contain other lists as elements. Think of them as multi-dimensional containers, like boxes within boxes, or a grid of data. A regular list is one-dimensional, like a single row of items. A nested list creates a two-dimensional structure, like a table with rows and columns. You can even nest deeper for three-dimensional or higher structures. Let's explore the various ways to create two-dimensional lists in Python. You can create 2D lists manually. Use list comprehensions for dynamic sizing. Initialize with calculated values. Reshape existing data. Or use helper functions. List comprehensions are preferred for creating empty matrices as they create separate list objects for each row. There's a dangerous pitfall when creating 2D lists that every Python programmer must understand. Let's see what not to do. The multiplication method creates multiple references to the same list object. When you modify one element, it changes all rows because they're all the same list. Always use list comprehension to create separate list objects for each row. This is one of the most common and confusing mistakes in Python. Understanding how to access elements in 2D lists is fundamental. Let's visualize the indexing system and explore different access patterns. In a 2D list, we use two indices. First for the row, second for the column. Element at position 1, 2 means row 1, column 2. Remember that Python uses zero-based indexing, so counting starts from 0. Access elements using double indexing, first index for row, second for column. Negative indices work from the end. Always consider bounds checking for robust code. Traversing 2D lists efficiently is crucial for data processing. Let's explore different traversal patterns and their use cases. Common traversal patterns include row by row for general processing, enumerate when you need indices, direct element access for simple operations, column by column for vertical analysis, and diagonal traversal for matrix operations. Choose the pattern that matches your data processing needs. Let's implement common matrix operations that you'll encounter in mathematics, data science, and algorithm problems. Essential matrix operations include addition for element-wise combining, transpose for flipping rows and columns, and multiplication for mathematical computation. These operations form the foundation of linear algebra and data science applications. Notice how we use nested loops to access each element systematically. 2D lists shine in countless real-world scenarios. Let's explore practical applications that demonstrate their versatility and power. Game development benefits greatly from 2D lists. Here's a tic-tac-toe implementation where the game board is a 3x3 matrix. We can easily check moves, validate positions, and determine winners by examining rows, columns, and diagonals. Image processing treats images as 2D arrays of pixels. Each pixel contains RGB color values. We can create gradients, apply filters, calculate brightness, and implement blur effects by manipulating these 2D structures. This is the foundation of computer graphics and image editing. Data analysis often involves tabular data represented as 2D lists. We can analyze monthly trends, find top-performing products, and create summary tables. Each row represents a record, and each column represents a different data attribute. Beyond simple 2D lists, you can create complex multidimensional structures for sophisticated data organization and modeling. Advanced structures combine lists, dictionaries, and other data types. 3D arrays handle multi-channel data like color images. Complex nested structures can model real-world entities with multiple attributes and relationships. This flexibility makes nested data structures incredibly powerful for complex applications. List comprehensions become incredibly powerful when working with 2D data, allowing you to transform, filter, and process nested structures elegantly. List comprehensions excel at 2D data manipulation. Create multiplication tables, transpose matrices, filter data conditionally, calculate transformations, flatten structures, and generate patterns. Nested comprehensions can replace complex loops while remaining readable and efficient. Working with large 2D structures requires understanding performance implications and memory optimization techniques. Flat lists are more memory efficient than nested lists. Direct iteration is often faster than index-based access due to lower overhead. List comprehensions are also efficient and concise for aggregations. Use cache-friendly iteration and lazy evaluation via generators to save memory when working with large datasets. Many classic algorithms work beautifully with 2D lists. Let's explore essential patterns and problem-solving techniques. Flood fill simulates the paint bucket tool, filling connected regions. Spiral traversal is a useful pattern for printing matrices layer by layer. The island counting algorithm helps find connected components in binary grids using DFS. Matrix rotation is a key operation in image processing in games for orientation changes. Working with 2D data can be complex. Let's learn essential debugging and visualization techniques to understand and troubleshoot your nested structures. Use a formatted print function to clearly inspect matrix rows and values. Use matrix info functions to get size, structure, types, and numeric stats. ASCII heat maps help visualize numeric patterns and intensity in 2D data using simple characters. You can automate checks for missing values, jagged arrays, or empty rows to detect issues early. Let's explore essential best practices and avoid common mistakes when working with nested data. Structures. Always validate matrix dimensions before performing operations. Check for empty matrices and ensure dimensions are compatible for the intended operation. Avoid shallow copies when working with nested lists. Use deep copy to prevent shared references. Encapsulate common matrix operations in a helper class to improve code reuse and safety. Never modify a matrix while iterating over it. Instead, construct the new filtered structure. Validate input types and structures before processing to avoid bugs and ensure reliability. Break down large matrices into smaller chunks to process them efficiently and avoid memory overload. While built-in lists are powerful, specialized libraries offer enhanced functionality for numerical computing and data science applications. NumPy provides a more efficient and powerful way to handle numerical matrix data. NumPy performs vectorized operations significantly faster than traditional Python loops. Pandas makes it easy to work with tabular data and perform quick analyses. NumPy supports powerful operations like matrix multiplication, inversion, and statistical analysis. Let's consolidate everything you've learned about nested data structures and matrix-like operations. In Python, key concepts include understanding 2D structure as nested lists, proper initialization techniques, double indexing for access, and essential operations like traversal and transformation. Applications span games, image processing, data analysis, and complex modeling. Performance considerations include copy behavior, dimension validation, and choosing the right tools for numerical vs. general purpose operations. Here's a comprehensive example that demonstrates nested data mastery. An image processor uses 3D nested lists for RGB data. Implements safe pixel access with boundary checking. Applies matrix operations for filtering. And uses nested iteration for complex algorithms. This example showcases initialization, access patterns, validation, and real-world application. Nested data structures are your multi-dimensional toolkit. From simple 1D lists to complex 3D arrays, they provide the foundation for sophisticated data organization. Whether you're building games, processing images, analyzing data, or solving algorithmic challenges, nested lists give you the power to model and manipulate complex relationships. Master nested data structures, and you'll master complex problem solving. Thank you for joining this comprehensive journey through nested data structures. You now understand 2D lists, matrix operations, complex nested patterns, and real-world applications. Practice with game boards, image processing, and data analysis projects. Remember, when your data has multiple dimensions, nested lists provide the perfect structure. Think in dimensions, code with confidence, and keep building amazing multidimensional solutions.